In this problem, we have two particles labeled 1 and 2 moving with constant velocities v1 and v2 along two mutually perpendicular straight lines toward the intersection point O. At the moment t equals 0, the particles were located at the distances L1 and L2 from the point O. Our task is to find when the distance between the particles becomes the smallest and what that minimum distance is equal to. Let's start by visualizing the problem. We'll set up a coordinate system where the perpendicular lines are the x and y axes, and O is at the origin. Particle 1 is initially at distance L1 from origin O along the x-axis, and particle 2 is at distance L2 from origin O along the y-axis. As time passes, both particles move toward the intersection point O. Let's see how their positions change over time. At any time t, the distance between the two particles can be calculated using the Pythagorean theorem. Now that we've visualized the problem, let's develop the mathematical framework to find when the distance is minimum. At time t, the position of particle 1 is L1 minus v1 times t along the x-axis, and the position of particle 2 is L2 minus v2 times t along the y-axis. Using the Pythagorean theorem, we can compute the distance between them as the square root of the sum of squares of their coordinates. To find when the distance between particles is minimum, we need to minimize this distance function. Instead of working with the square root directly, we can minimize the square of the distance, which is easier mathematically but gives the same result. To find the minimum, we take the derivative with respect to time and set it equal to 0. Let's solve this equation to find the time when the distance is minimum. Simplifying the derivative equation, we get negative 2v1 times L1 minus v1t minus 2v2 times L2 minus v2t equals 0. Expanding these terms, we have negative 2v1 L1 plus 2v1 squared t minus 2v2 L2 plus 2v2 squared t equals 0. Solving for t, we find that t equals the sum of v1 times L1 plus v2 times L2, divided by the sum of v1 squared plus v2 squared. Now that we have found the time when the minimum distance occurs, let's calculate what that minimum distance is. At this optimal time, the x-coordinate of particle 1 is L1 minus v1 times t, and the y-coordinate of particle 2 is L2 minus v2 times t. Substituting these into our distance formula, we get the minimum distance between the particles. Let's visualize this solution with our diagram. As the particles move towards the origin, the distance between them first decreases, reaches a minimum, and then potentially increases if the particles continue past the origin. The minimum distance occurs when the line connecting the particles is perpendicular to both velocity vectors. To summarize our solution, the distance between the particles becomes smallest at time t equals v1 L1 plus v2 L2, divided by v1 squared plus v2 squared. And the minimum distance between them equals the absolute value of v1 times L2 minus v2 times L1, divided by the square root of v1 squared plus v2 squared. This elegant solution demonstrates the application of calculus to physics problems involving motion.